So, hi everyone. My name is Eric Coughlin. I'm from Syracuse University in New York, where I'm an assistant professor. I'm also one of the people who is organizing this program on tidal disruption events, or TDEs, as Kate was just discussing. Last week we had a whole 4-day conference dedicated to the subject. I feel kind of TDE'd out, and I have 3 more weeks to go. But today, what I want to start off with in this teachers conference is kind of what I want to kind of do is take a little bit of a step back and look at sort of the physics of black holes, but motivated by and sort of in the context of something that we all know and love, which is our beloved Newton's second F equals ma. So just to give you a brief overview, very brief overview, I really have just 2 things that I really want to talk about today. The first is how we think about black holes in the context of our most kind of complete theory of gravity to date, which is general relativity, which tells us that black holes, gravity and consequently black holes are really manifestations of something called curvature. And to be clear, I'm not going to try to cram an entire course on general relativity into this 50-minute time slot. But as I said, what I'm going to try to do is sort of show you how curvature can actually be kind of a weird thing to quantify, and you can maybe trick yourself into thinking that the space in which you live is curved when in actuality it may not be. And then toward the end, hopefully I have time depending on how many questions I get, at the end what I'm going to describe is how, and Kate already alluded to this as well, how black holes can actually be some of the brightest objects in the entire universe. And of course I'm being slightly misleading because it's not the black hole itself, it's actually the stuff around the black hole. But I'll describe just the very basic physics of where that statement actually originates. And then actually, I don't have it on here, but if I have time at the very, very end, I'll talk about a few initiatives that I'm involved with high school physics teachers and also students. All right, so let's get going. So black holes, you're all aware of the phenomenon of a black hole. They're in the media all the time. And what you may also be aware of is that there's actually a very nice derivation you can do of what a black hole is that uses very classical physics. It's physics that you all know, right? This involves the escape speed. Okay, so this is an expression that you probably use in your physics classrooms. The very basic idea is that if I'm standing on the surface of some object of mass m and radius r, there's some speed with which I need to launch something from that surface in order for that object to escape from the gravitational field of the object on which I'm standing entirely. Okay, so if you plug in numbers for the Earth on this, you find that the escape speed for the Earth is about 11 kilometers a second. Okay, but what I want to do, right, is I want to kind of consider the hypothetical scenario in which I construct an object such that its escape speed is equal to the speed of light, right, where the speed of light is this incredibly fast 300,000 kilometers a second. You could go from here back to Syracuse in the blink of an eye if you can move at this speed. Okay, so what we do, set the left-hand side equal to c, square both sides, rearrange some things, and what you can solve for is the size that this object, or the radius that this object would necessarily have if this were going to be the case. Okay, so if the object is this small, okay, I could go onto its surface, shine a laser beam upward, right, and the laser light would initially move at the speed of light, but it would start to decelerate, right, in the gravitational field, it would move out, and eventually it would stop. If you plug in the mass of the Earth into this expression, anybody know how small it would be? What radius you get? Yeah, centimeter. I saw someone say it. Yeah, centimeter, right? So you have to crush the Earth down to the size of a centimeter in order for this to happen. So that's ridiculously dense. And for this reason, a lot of people kind of thought that this was insane and would never happen. But at the same time, this is really kind of a strange concept when you really sit down and you think about it for a while, because I never actually specified anything about this hypothetical object aside from its physical properties, namely its mass and its radius. And so this object could be, for example, a star. Okay, a star like our sun, and a star emits a whole ton of energy from its surface in the form of light. But according to this simple little thought experiment, none of that light would actually be able to reach an outside observer, right? And so this object would be something like a dark star, which is very strange. Does anyone know who was the first to think about this, come up with this weird conclusion?
John Mitchell.
John Mitchell, that's right. I knew you would all know this. Okay, so this is John Mitchell in 1783, and then Laplace on the order of 10 years later. This predates Einstein by about 130 years. Okay, but it turns out that this is very wrong. Okay, the idea of thinking about light going out to infinity and eventually stopping is not at all the way that we think that black holes actually work. And in order to do this better justice, we really need to understand the way that gravity works. According to our best theory of gravity to date, which we call general relativity, and this is right according to Einstein, his famous publication back in 1915. We just passed the centennial about 10 years ago. There was a big to-do at the AAS. It was really fun. Okay, and again, I'm not going to try to do a whole course on general relativity. I'm just going to try to motivate where this idea of curvature really comes from and how it manifests in the context of a gravitational field. Okay, so let's go to something that we're all very familiar with, right? We all tell our students F equals ma, and according to Newton, F is equal to minus mg, okay? G is a vector, gravity, that points down toward the floor, okay? And so if F is equal to ma and F is also equal to minus mg, I equate these two things, of course, and what I arrive at is that the acceleration in the gravitational field of any object is the same, it's just minus g, right? Independent of its mass. And already, this is a really fundamental and very cool statement, right? It says that the rate at which an object accelerates in a gravitational field is independent of its inertial mass. And that's really surprising. And from this results the wonderful world of projectile motion that we make all of our students go through on a semester by semester basis. Okay, but I'm not going to do that with you here today. Instead, I'm going to do something that's very simple. I'm just going to take this minus g over to the other side. Write this as a plus g equals 0. I'm going to define a plus g as some new quantity. Let's call it a prime. And by just going through some very simple manipulations, what I seemingly arrive at is this statement that a prime is equal to 0. Okay, and this just comes from F equals ma. Okay, so it doesn't really seem like I've done anything too earth-shattering here. But what this actually says is that if I now go into the frame that is freely falling in my gravitational field, what I actually do is I remove the apparent force of gravity. Okay, so if I drill a hole through the center of the earth and I jump in, right, and then you jump in after me, we're both accelerating at the same rate, what we actually see is the other person moving away at a constant velocity, right? And that's Newton's first law, right? Objects move at a constant velocity when they're not acted upon by a force. And so by just doing this very simple coordinate transformation effectively, by accelerating appropriately, I've actually removed the existence of gravity. And it gets even weirder when you think about, well, imagine that I was never even standing here on the surface here at all, right? What if I was just freely falling the entire time? I would never know that there was a force acting on me, and I would never even define gravity to be a thing in the first place, right? And so that's a very puzzling kind of conclusion to come to, right? To say that actually if I'm falling in a gravitational field, I'm really not accelerating at all. I'm not acted upon by a force, right? That's very confusing. And the reason that we're able to do this is because of this equivalence between the inertial and the gravitational mass, right? There's nothing intrinsic to the property of the object that I need to assert in order for this statement to be true, right? And the same statement is not true for something like electromagnetism, right? You need charge, something intrinsic to the object to actually experience the force. Okay, so F equals ma, right? Our beloved expression. So Newton tells us that gravity is on the left. F is equal to minus mg. Gravity is a force. But what Einstein kind of realized is that by making just a very good choice of change of coordinates, essentially, I can do away with gravity entirely, right, at a point, right? I can always make the right acceleration and do away with the force that I experience if I'm clever about it, right? And so in a neat kind of way, what you can say is that according to Einstein, gravity actually appears on the right-hand side of this equation, right? You can actually lump gravity into the coordinates that I choose in the way that I accelerate, which is a very strange way to think about it. But this is what he was kind of getting to and realizing, and it's very uncomfortable, right? It's very weird because you're thinking the whole time about gravity as being a force, but suddenly I can just move around and accelerate in different ways and kind of do away with it entirely, right? Or I can bring it back, like in a centrifuge, right? Suddenly you feel the wall pushing against you, and it's kind of like you're in a gravitational field, right? And all those ideas where, you know, how do I distinguish acceleration from gravity? All these types of ideas. Okay. So this statement that, right, a prime equals 0 is a local statement, which means I can pick a point in my space and I can remove the effects of gravity at that one location. But we know, right, g is equal to 9.81 meters per second squared. That statement is only true at the surface of the Earth. And more generally, right, Newton also said something else about gravity, right? He gave us his famous law, Newton's law of gravitation, the inverse square law, which says that if I start to move around in my space, what I notice is that the force of gravity starts to change, right? And it changes in a very specific way as a function of my coordinates, right? This little r that's appearing here between, which is the distance between me and the object that's doing the gravitating, right? The Earth in this case. So while this statement, right, that I can always locally transform away the effects of gravity is true, it doesn't quite tell us all the same information that Newton's second law does, right? It doesn't tell us how gravity behaves as a function of position throughout space. And you can kind of think about this a little more, right? Let's imagine that I go out in space, right, and I measure some force that's acting in some direction, and then I fire my jetpack and I move around. If I'm in the gravitational field of the Earth, what I see is that there's a change in the directionality of the force that's acting on me, right? So the gravitational field that I experience changes as a function of my position as I move around in a true gravitational field. On the other hand, if I'm in, like, you know, in this famous thought experiment that Einstein apparently did, right, if I'm in an elevator and I'm being pulled up by some imaginary giant hand, right, and I feel the force on my feet, if I start to move around, right, and I try to detect changes in the force that I experience, and I detect none, what that tells me is that I can actually just establish a uniform acceleration that doesn't change in any way and completely do away with that effect entirely, globally, right? And so these two things are actually slightly different, right? And what Einstein effectively asserted is that the left-hand side is true gravity, right? True gravity changes as a function of the position as I move around in space. I have to do different things to my acceleration in order to remove it. And this is also what tidal effects are, right, which we're going to hear a lot more about, which Kate already mentioned, right, the tidal force. Okay, that's the difference in the force across the size of a body. This is, in a way, a manifestation of true gravity according to Einstein. Whereas the right is not, right? The right is not gravity, it's really just acceleration. Okay. All right, so from this, we make like two really remarkable claims, okay? So this gravity is indistinguishable from a point. Sorry, gravity is indistinguishable from acceleration at a point. What that translated into is the notion that space is locally flat, meaning that we always see at our point the speed of light as being the same value, okay? And that automatically invalidates the argument we were just making a few slides ago, what John Mitchell was saying, right, which is that light was going to be decelerating as it propagated away from this hypothetical object. The second statement is that gravity is distinguishable from acceleration as I start to move around my space, right, and as I start to see changes in it as I sample my little tiny region wherever I might be. And what that led Einstein to conclude is that that's very analogous to the notion that space is curved in the presence of gravity. Okay, and I'm not like justifying these statements, right? I didn't come up with them, but this was the insight that Einstein really had, right? Which is like kind of amazing when you start to think about it, and what I'll try to show. And what this says is that gravity is a manifestation of, or is kind of the same thing as curvature in our space. Okay, and at this point you probably see some nice mesh, right, with like a sun, and there's like a dimple in it, right? And that kind of nicely fits in with your picture of what curvature is, right? It's bendy stuff, you know? Okay, but what actually is curvature, right? How do I quantify the notion of curvature? Okay, and so I have just three questions that might show that this is not such a simple thing to do. Okay, so what do you all think? So normally when I'm like in my classroom, I like to do these like ABCD card things and have the students respond, but I didn't feel like making you all try to download an app. So what do we think? Is the orange shape up here, is this curved or not? I think I agree. Okay. Okay, what about this one? Okay. What about that one? Okay, so like, I don't know. Right? So what I would actually argue is that this is actually not curved. And the reason is that I can go over to my blackboard over here. Okay, so my blackboard, you'd also probably agree, we all agreed that that plane back there was flat. The blackboard is also flat. All right, so I can fill up my flat space with a bunch of curves, right? But that doesn't actually make my space curved, right? The blackboard itself is still flat. So there's something strange here, right? And I agree with all of your intuition, right? To me, it seems like that's definitely curved, and that's definitely flat. But what is it about these spaces that actually makes that curviness, you know? And it turns out that that's really a really hard problem to do. But I'll show you how you might be able to try to figure this out. And there's actually a really kind of important thing to realize, which is that in going from this to this, what you can imagine is that I can just take my nice flat plane and I can just bend it, right? And my plane is a two-dimensional object, right? So the dimensionality is defined by the number of coordinates I need to span my space, right? So I can tell you where you are in X and Y, and I can get all the way around in my flat space. The shape here is also two-dimensional, right? And we know that actually because we live on the surface of the Earth, and to get anywhere on the surface of the Earth, you only need latitude and longitude, right? And those are two coordinates. So again, that kind of defines the dimensionality of my space, the number of coordinates I need to get around, and the same remains true here, right? I'm still a two-dimensional surface, but the problem is that in order to visualize the fact that this thing is actually curved, I needed to bend it in a third dimension, right? And that gets really kind of problematic when you start to think about if you could actually measure the curvature of the space in which you live, right? And there's all these, like, you know, this is really a wonderful way to think about how curvature could be measured, right? If you were an ant living on the surface of this sphere, would you actually be able to know that the space in which you live is curved, right? And the problem, obviously, is that we live in three-dimensional space, I'm pretty sure, and I can't visualize bending three-dimensional space into a flat fourth dimension. So there has to be some way for us to be able to figure out that we're actually living in a curved space, intrinsically, right? Intrinsically, like meaning within the space itself. And so it turns out no, right? You can actually do this, and there's a really neat way to do it, right? I would say, okay, I'm going to start here, and I'm going to construct what I'm going to call my local flat coordinate system, and I'm going to walk in the straightest possible line that I can, which is that I'm not going to deviate the directionality of my coordinates as I continue to move. And I'm going to go, and I'm going to go, and I'm going to go, and I'm going to keep walking and keep walking. I'm going to go a really far distance, and then I'm going to turn 90 degrees, and I'm going to walk a little distance this way, and then I'm going to turn 90 degrees again, and I'm going to walk back in the same way that I came, right? And if my space is flat, right, one of Euclid's postulates tells me that these two parallel lines that I just traced out are never going to cross, right? Or to say it another way, the distance that I would measure, right, like let's say I get back here, I could measure the distance between my two parallel lines, and then I'd go down here and I would measure the distance again. They always remain the same distance apart, okay? It turns out that that statement is not actually true when your space is curved, okay? And so this is something else, so I really love this programming language called Mathematica. It's not super popular among the astronomical community. Okay, so this is a lot bigger than when I looked at it this morning. All right, so this is what this actually shows. Okay, so I'm going to start at the North Pole here, and I'm going to take a paintbrush behind me, and I'm going to walk in the straightest possible line that I can. I'm going to start to move downward. I'm going to go all the way down to something like the equator. I'm going to hang a loo, right? I'm going to walk a little bit. I'm going to start moving back in the same way that I originally came, right? And these are the straightest possible paths that I can construct, where I'm what's called parallel transporting my locally flat coordinate system along with me as I move. Okay, so it's a very specific set of operations that I'm doing here on the surface of the Earth, of this globe, right, that's intrinsic to that space. And what you can see is that as I keep moving along this path, right, here at this point, I could turn again, and I could measure the distance here, and I could go back to where I started and keep going. And what I would find is that these straightest possible paths actually start to converge, and they actually come back to a point, right? And so if the other way to say this is that triangles that are drawn on the surfaces of curved objects, the interior angles don't actually add up necessarily to 180 degrees. And you can see that here, right? Because I went 90 and I went 90, but I'm going back to something that's not 0, right? And 90 plus something that's not 0 is greater than 180. Okay? And that's what's so cool about this, right? This is really neat, right? This is something that I can do within my space, and I can figure out that it's curved. And you can also see, so I said something before, right, about how space is locally flat. So at any given point in my curved space, I can do something similar, and I can construct a concept known as the tangent plane, right? I can always draw a plane at any point, any single point in my curved space that sort of kisses the surface at one single point and is thereby locally flat, right? And so that's this idea, right, is that at a single point, I'm always justified in saying that I'm in flat space, but as I start to move around and I see subtle little differences, that then tells me something about the curvature, the intrinsic curvature of the space in which I live. Okay. And this is then where, okay, so like, I haven't said anything about gravity, right? All I'm doing is stupid geometry problems and whatever, right? But this is where like the insight comes in, because this is the same thing that I was just showing you, right? As I'm moving along in my straightest possible paths on my sphere, the distance between these straightest possible paths starts to change. And what Einstein realized is that the same thing is actually kind of true when I have two inertial observers that are just freely falling in a gravitational field, which is shown here, right? As I was saying, the force due to gravity is slightly different, right, from point to point. And so if I start to free fall and follow my straightest possible paths, the distance between things is actually going to start to change, right? And so Newton's first law, right, things continue to move in a straight line, right? Apparently that's only true in flat space, is what Einstein was trying to say. And so if you want to sound fancy at a party, okay, this is called geodesic convergence. Geodesics are the straightest possible paths in a curved space. And this is, again, a manifestation of gravity and simultaneously indicates the curvature of the space in which we live, which is just like such a beautiful, I don't know, people say that math and physics is beautiful. It's really just an elegant formulation of the way that gravity works. Okay. All right, but we still haven't really achieved what we set out to do originally, right? We still need to know where this curvature actually comes from, right? So how do I get back to Newton's second law, right? How do I generate curvature? And the idea was to say that the presence of mass and energy is actually what generates curvature. So there's some proportionality between these two. And I'm not going to go into really any detail about this, but to quantify this, we hypothesize and then ultimately try to solve what turn out to be a very hard set of equations to solve. These are known as Einstein's field equations. Okay, so on the left-hand side of this is what you're going to call curvature. Okay, and the r mu nu, the mu nu as the superscripts, this is really just notation. It's called index notation. This is like up there with one of like the 3 things that I learned that have been most useful to me throughout like my entire career. When I realized you could do this, instead of writing things Instead of writing vectors with little arrows on them, you can use this index notation. It's extremely useful, actually. And on the right, in particular, this t mu nu thing, okay, this is another, you can kind of think of as a vector. There's actually 10 independent equations contained in that thing, which actually shows you the power of this index notation, actually. The right-hand side is the stuff, okay? This is the mass and the energy. And so, which are the same thing. But, so the right-hand side is representing how much stuff you have. And the left-hand side is, in a very complicated mathematical way, it turns out, quantifying how much curvature exists as a byproduct of the existence of that mass and energy. And what's really cool is the proportionality constant between the two, right? This factor of 8 pi g divided by c to the fourth. Because g is a small number, right? 6.67 times 10 to the minus 11 in your MKS system. C is a very big number. And g divided by c to the fourth is therefore an extremely small number, right? So in CGS units, which are the favorite of astronomers for reasons I don't know, that's 2 times 10 to the minus 48, which is an unbelievably small number, right? Okay, so the way to say that is that space-time is really stiff. It takes a whole lot of stuff to bend it just by a little bit. Okay. So these are Einstein's field equations. In a GR class, you'd go about solving these, and you'd write down like the Riemann tensor and the Ricci tensor and a bunch of things called Christoffel symbols, and it would take us forever. Okay, but let's just get to the punchline. It turns out that in certain situations, we can actually solve this set of equations. Okay, and we've already been asking about rotating black holes and things. Okay, so rotating black holes are a specific kind of solution to Einstein's equations, which is called the Kerr metric. Roy Kerr, it was discovered in like 1963, I think, 1964. I don't know, fact check me on that. So the Schwarzschild, and remember, right, Einstein published the field equations in 1915. Okay, so that's like 50 years after the fact. It was actually the same year that Einstein published his equations that the Schwarzschild metric was recovered. And what this does, so the metric is kind of the quantity that tells you how space, or how distances change from point to point as I move around within my space. Remember, which is the thing that we're saying is tightly coupled to the existence of gravity. There's this changing distance as I move around. And what it does is it describes the space and also the time around an object of mass m that's just sitting there to some far off distant observer. Okay, and so how would so now, okay, now we're in a three-dimensional space. Okay, we're in some metric in some gravitational field. And how do I now go about doing this thing of measuring the curvature of space? Okay, so one way is to look at the orbits of objects as they move around, according to a distant observer, right? What would these orbits actually look like? Okay, and so these are ellipses in Keplerian, in Newtonian gravity. But in general relativity, they're actually not quite closed ellipses, right? And this is all spatial, right? And actually, the fact that they're not closed is extremely important for TDEs, as Brenna may mention. I don't know if Brenna's here. Yeah, maybe she'll talk about it. I don't know. But these are like spatial concepts, right? You're looking around, you're seeing how positions are changing, what sort of trajectories that they trace out, and that's all fine and good. But there's actually another interesting way to do this that involves the concept of time. And this is where things get really wacky and really hard to appreciate how confusing that this really is. And so here's one way we could do this. So you and I could stand some far distance away from some object of mass m. Okay, so we're now in the Schwarzschild metric. And we could synchronize our watches. And I could say, okay, here's this laser beam. I want you to take this laser beam with you, and I want you to go down relatively close to this object of mass m. And I want you to shine at me your laser beam, little quick pulses that are separated by some time, let's call it delta t prime, according to you. Okay, so this is the thing we could definitely do, right? You go stand over there, and you look at your watch, and you go, bent, 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 right? And you're just shining pulses of light at me. Okay, and I'm going to stand over here, and I'm going to look at my watch, and I'm going to measure the time between when I see these pulses. Okay, and there's no motion between us. That actually makes things a little bit more complicated. But you're just going to sit there stationary, And we're going to do that. And your intuition says time is universal, right? And so naturally, the time between when I measure these pulses, the time between them, let's call that delta t, right? That has to be the same as the time between when you're shining your laser beam, right? 1 second's got to equal 1 second. And it turns out that this is wrong, okay? So it turns out in a curved space-time, these lengths of time that you and I measure are actually going to start to differ. And the thing about the Schwarzschild metric, right, having this solution to Einstein's equations actually tells us exactly how these two things differ from one another as a function of our position throughout our space, which is so cool, right? And it's through this wonky little factor down here, okay? So this is 2gm over rc squared. You can see we're getting back to that thing that I introduced on one of the first couple slides, okay? So this is 1 minus some number, okay? So this is less than 1. 1 over that is greater than 1. So delta t, the time that I measure on my watch, is actually always longer than the time that you are taking to send your pulses, right? And this is time according to you. So time according to me is slightly longer than the time according to you. Doesn't make any sense, but okay, fine. Right, we're going to just adopt that. And you'll notice, right, so as you, right, so this is a proxy for your distance away or your position from this object of mass m. So as you start to get closer and closer to this distance away, this 2gm divided by c squared, my delta t, right, and this is the crazy thing, right, you're just sitting there and you're just sending me signals one after the other at 1 second apart according to you. But as you get closer, I start to receive those signals separated further and further in time. But if you think about it, this is just like the rate of passage of time itself, according to us, right? Like this is one way that I would like, tell how much time is going by according to my watch. This is how I'm measuring the time. So what this is actually saying is that my clock is in some way running fast relative to yours, right? And so if you've seen the movie Interstellar, there's this scene, right, where they go down to this planet that's very close to the supermassive black hole. They come back some number of hours later, according to them, whereas the person who's been left on the spaceship has aged by something like 15 years, right? And this is a real effect, and due to general relativity and this notion of curvature and the warping of not just space, but also time. And it's extremely confusing. Okay, so you can make a plot. We all love plots. Okay, so this is the ratio of my time as a distant observer relative to your time, the time between your pulses that you're sending to me. Okay? And it obeys this funky little radical, and you can plot this, right? And it diverges in the limit that you approach this special distance. Okay, and this concept is known as gravitational time dilation. And what it shows is that time for me, right, the time that I measure goes to infinity in the limit that you approach this special distance, 2gm divided by c squared. Okay? That means that as you get closer and closer, I would start to receive your signals farther and farther stretched out in time. And as you approach it, I would actually never receive another one. Okay? So my time diverges as you go beyond this 2gm over c squared. Points in space and time are what we call events. And so this distance, 2gm divided by c squared, is kind of like the farthest reach of my coordinates as an outside observer. It's the farthest they can go. They don't penetrate interior to that as an outside observer. Okay, this would be like the horizon. It's the farthest I can possibly see. It's on the horizon. And it's for this reason that we call this special distance the event horizon. It's also a really crappy movie from like late 90s. And so now, okay, so now this is what's really cool, right? So we derived actually the same thing that was derived by Laplace and John Mitchell back in the late 1700s. But now the interpretation is very, very different, right? This is actually a distance away from some object of mass m, beyond which we cannot go, right? And from which nothing will emerge, okay? And so this is the concept of a black hole, right? And what I think is really neat is that it's deeply embedded in a lot of these concepts related to geometry and just time works, and it's all very, I don't know, very conceptual and fun to think about. Okay, so let's get back to some astronomy and astrophysics. Okay, so let's imagine a slightly different scenario where we're standing in the same spot and I just kick you into the black hole. Okay, so you're now falling into the black hole. So now you have some velocity, v, and this expression, this is the same thing I had before, but now it starts to become slightly more complicated because we're starting to move. And, you know, this might look weird and unfamiliar. It probably does. It was unfamiliar to me when I derived it. It's also probably wrong, but, you know. But you can actually regain some sense of, I don't know, similarity with something that you may have seen before if you just set the mass equal to 0 in this expression. Okay, now it's just you and me moving away from one another at some speed v. And what this reduces to is something called the Doppler shift. Right? So if something is moving away from me, I will actually receive your signals at a slightly later, slightly longer time intervals, because the light you're sending me has to make up an extra little distance as you're moving away from me. Okay, this is the Doppler shift. And this is now what becomes really cool in the context of astronomy and observations and actually measuring the properties of black holes. Because in some sense, if we have a prescription for the velocity, how the velocity behaves as a function of distance from the black hole, we can write the entire right-hand side of that expression as a function of r divided by gm. And if we can actually measure the differences in these times, I can actually figure out where you are from the black hole as this whole thing happens. And this is something that we can actually do in astronomy and astrophysics in principle. Okay, and so this is actually, I'm showing you the frequency here of light emitted, but it's all these same effects. Okay, so this is a famous paper by Andy Fabian. Right, it's showing how when something gets really close to a black hole, when you get really close to a black hole and you're shining your laser beam, lots of strange things start to happen to the properties of the light that you actually emit. Right? All right, but hold on. I never said anything about, I mean, we're just talking about black holes and shining lights, right? Like, yeah, it'd be great if I could send you off to a black hole and kick you in and you could send me signals, right? But that's not going to happen anytime soon, right? So what is actually providing the light? Okay, and so Kate already kind of started off this discussion a little bit ago, right? And that's where we get to this concept of black holes being some of the brightest objects in the entire universe. All right, so now that I just told you that gravity is not a force, it's actually this property of space and time and curvature, and we have to solve the field equations, let's forget all about that, okay? Let's go back into the wonderful world of Isaac Newton. And what I want to imagine is that I have some object of mass m and some other object, this little blue one, that's just orbiting about that bigger object, okay, on a circular orbit. All right, so F is still equal to ma, thankfully. So in this case, I'm on a circular orbit, so I have my centripetal acceleration, a is equal to minus v squared over r, where v is my velocity, r is my distance. The gravitational force, okay, again, according to Newton, minus gm1 m2 divided by r squared. Of course, I can set these things equal to one another. And what I derive, and what's going to be useful for us, is that the kinetic energy of this thing is just equal to 1/2 mv squared, of course. But then if I write that in terms of the properties of my distance, it's just gmm divided by 2 times my distance. Okay, so that's my kinetic energy as a function of my distance away from my, let's call it a black hole, because why not? All right, I can also calculate the potential energy. Okay, this is just minus gm m divided by r. Again, we're writing the potential energy as a function of distance. And what this shows me is that my potential is actually minus twice my kinetic energy. And then I can add them together, and that shows that u plus 2k is equal to 0. And this is actually a specific example, or a simplified version, of something called the virial theorem. Again, if you want to sound fancy. All right, so now what I want to imagine is that by some process, I allow my object to sink a little bit into the gravitational potential of my black hole. Okay, it goes from some radius r1 to some smaller radius r2. Okay, so the above expressions have to hold for both R1 and R2. I can now take the difference between these two. So delta U is just U2 minus U1. Delta K is K2 minus K1. And that tells me that delta U plus delta K, 2 delta K, sorry, is equal to 0. But wait a minute, right? My total energy is equal to the sum of my kinetic and my potential energy, right? So I can put delta U plus delta K is equal to 0. Delta U plus delta K is equal to delta E. And therefore, delta E is minus delta K. Okay? And the weird thing about gravity is that as I sink deeper in, as I get closer, I actually speed up, right? I get faster. So gravity has like a negative specific heat associated with it, which is really bizarre too. All right? So my delta K is actually greater than 0. I'm going faster now that I've gotten deeper in. And that means that in doing this, in going from some farther distance to a smaller distance, I've actually lost some energy. But I can't lose energy, right? Like, energy had better be conserved. I mean, I'm not going to throw that out the window, right? Okay. So what's going on here, and what we're seeing, is that this type of process can't happen while you simultaneously conserve energy. Okay, you've got to find some way of giving up your energy in order to make a transition like this, in order to sink deeper into a gravitational potential well. Okay, you go deeper into the gravitational potential. But we can kind of imagine, you know, what would be the case if some hypothetical mechanism existed that actually allowed me to do this, right? How much energy would I actually have to lose as I fall into my black hole? All right, so let's assume initially that I'm very, very far away. So my distance from my black hole is initially effectively infinity. Okay, then my initial distance, or sorry, my initial energy is basically 0. And as we just talked about, right, so now that means that the change in my total energy is just dependent on where I end up. Okay, it's just my final distance away from my black hole. But as we just talked about, the neat thing about black holes is you can get really, really close to the horizon, where your velocity is very, very close to the speed of light. And if you just plug R2 is equal to gm over c squared, and I'm of course forgetting about factors of 2 because we're all astronomers, okay, what this tells me is that in going from very far away from my black hole to very close, I have to give up half of my rest mass energy in the form of something, right? So you can sort of think about this. Again, hypothetically, some mechanism exists in the universe that allows me to do this. What this tells you is that I take in with me my rest mass energy, and I have to give out of the order half of that energy in doing so. And you can define an efficiency, right, from the energy out given the energy that I put in. And this tells me that by sinking deeper into a black hole, I've created essentially an extremely efficient engine, right? A way of extracting energy. Again, assuming I can find a mechanism that does this, that lets me do this. And you can compare this to some of the other most efficient, energetically efficient processes in the universe, one of which is nuclear fusion occurring in the core of our sun via a process called the proton-proton chain. You can work out the efficiency of this. You want to slam 4 protons together. You get some energy out. That energy, this efficiency is on the order of it's less than 1%. So what this is showing us is that just by sinking deeper into a gravitational potential, right, just by getting, if I can, just getting very close to a black hole, I give up an enormous amount of energy. And in this way, black holes are among the most efficient engines, the brightest objects in the entire universe. Okay, but we got to figure out what actually enables us to do this. Okay, and the answer is what we think. The answer is actually viscosity. Okay, so as I said, right, objects in a gravitational field are actually moving at a faster rate as they sink deeper in. Okay, what that implies is that there's shear, right? There's a relative velocity as I go from orbit to orbit and I sink deeper into my gravitational potential. Okay, so shear is relative motion. And if you rub your hands together really fast, right, you create a large amount of shear, but you also feel your hands get really hot, right? And that's dissipation. So that's viscosity, right? Viscosity is trying to dissipate the kinetic energy of my hands and turn it into heat. And so the idea is that with some form of viscosity, we can actually enable this process to happen. Material can sink deeper into a gravitational potential well, and in the process get extraordinarily hot and radiate enormous amounts of energy. Okay, and this is the accretion paradigm. This is what Cambridge is famous for. Back in the late 60s and early 70s, Donald Lindenbell, Jim Pringle, and Martin Rees. Okay, so quantitatively, a number of people, so probably the most famous one, right, the Shikurin-Sanyaya disk model. There's a very specific prescription for the type of viscosity that we employ. It's called the alpha disk model. This paper has over 10,000 citations. What exactly the form of the viscosity actually is still a question that we're really kind of trying to address. Most people think that it comes at least partially in the form of what's called a magnetorotational instability. So if you thread a gaseous collection of particles with a magnetic field, there's actually an instability that drives turbulence. And there's some turbulent dissipation that allows this material to give up energy and sink deeper in, and thereby transport angular momentum outward. Okay, so this is actually from a simulation by Jake Simon, Chris Beckwith, and Phil Armitage, who were all at University of Colorado at Boulder when I was there a little while ago. Okay. So there's one final step, one last thing that we have to address, right? Which is that it's actually not the black hole that does all the light giving off, as you might hope, right? We actually need some gas. So I need to dress up my black hole with some gas to make it shine. So where does that come from? One place is when you tidally shred a star by the gravitational field of one of these black holes, especially the very massive ones. And that's what Brenna, I think, is going to take over talking about. And that's effectively where I'm going to end. I'll just say that there are a couple of things, few things, that I'm pretty actively involved in the context of working with high school students and also high school physics teachers. So the top one is called Syracuse University Research in Physics, or SURF. So this is a program where we actually bring somewhere between a dozen and 20 or so high school students in from the Syracuse City School District to do research with physics faculty in our department for about 6 weeks over the summer. And they get like a paid, so it's paid, and they also get free meals and transportation. And it was recently just funded by a really nice grant from the NSF, which I actually didn't apply for. It was actually our department chair. I also work with a local high school art teacher on some really fun kind of representations of various astrophysical phenomena. We're actually working on time right now, which is really weird and hard to do. And then finally, there's something called SUPA, so Syracuse University Project Advance, which is actually a partnership between Syracuse University and high schools actually all around the state, where high school teachers are trained to basically teach intro physics classes from Syracuse University that then enables students to get college credit for these courses. So with that, I will finish up and I will take any questions. Thanks.
All right, thank you, Eric, for that great introduction. We have time for some questions. I'd like to remind people, please come up to one of the microphones or we'll bring you one so that your questions can be heard for the recording. Yeah.
Hi. Going back to the delta T prime, there's a certain R.
Yeah.
If it gets below a certain amount, of course, you're inside the event horizon, but then delta T becomes imaginary.
That's right.
What does that mean?
So it means that my delta T can't extend beyond that location. That doesn't necessarily mean that you can't pass through the horizon, which is very confusing. So this means, so you may have heard like some people say, like as to an outside observer, someone gets pasted onto the event horizon as they fall closer and closer, right? So that's according to an outside observer. But according to you, you could actually fall straight through and have no problem. I mean, you'd have problems, but you know. Right, so what I mean by that is you could just continue to look at your little watch, and you would see time progress normally. You'd also still see light moving at the speed of light as you did it. Yeah. So yes, very confusing.
Thank you.
Yeah.
Thank you for that. So one question I have is if time is basically slowing down as you approach the event horizon, it's kind of a follow-up to Eric's question here, then how does the black hole even form? Because as those pulses are getting slower and slower, at least from the perspective of the outside observer, I've realized the spaghettified
Yeah,
person goes through, but how does it even form at all so that us outside observers are observing an actual black hole?
Yeah. No, that's a very good question. So it's really, this is related to, and I'm not sure I'm going to have the perfect answer for this, but it's really like, the dynamical formation of a black hole involves the creation of an apparent horizon that then eventually shields the outside universe from what's within. And so it's actually a very dynamic process, and there's time dependence of the metric itself, which is really not accounted for here. So really, I guess what I'm saying is, when you fall into the horizon, the mass actually changes by a tiny little bit, which means that my event horizon actually grows ever so tiny, and that's not actually accounted for in a lot of what I'm talking about here. So that kind of makes sense.
There's a question up here. Can we get the...
Maybe we'll get the mic there. There are a couple over there too.
Oh, okay, cool.
Sorry, I had another question. This is a question about the geodesic convergence, that thought experiment where things are falling together. I've always had a hard time explaining this to myself or my students, which is, if light follows along straight paths through curved space-time, what's a nice way to explain why massive and massless bodies follow different paths through curved space-time?
I don't think I have a good answer for the reason why. I mean, I could, excuse me. The difference comes in, I guess, with what's called the proper distance. And so it's not actually, the thing that's kind of conserved is not actually just the physical distance, it's actually the distance minus something that has to do with time. And essentially what that demands is that light is always seen as moving at the speed of light in the locally flat frame. And so that kind of special distance is identically equal to 0 for massless particles, and it has to be for photons because they always have to be seen moving at the speed of light. Whereas it's not exactly equal to 1, it's not equal to 0, sorry, for massive particles. That's not a good answer.
So could we, I mean, if I were to totally just, could I say that the difference in the space paths would be analogous or the same as or kind of opposite to the difference in their paths through time?
So,
such that they followed the same space-time path?
So photons don't, there's no time according to photons.
Right.
So not quite. I don't know. We should just, we should talk about it. I would love to try to figure this out. Well, they're asking me very hard questions.
So the field equations work. Newton's universal law of gravity works. Is there a way to take the field equations and make some assumptions so you arrive at Newton's universal law of gravity?
So that is exactly what is done to arrive at that coefficient of 8 pi g divided by c to the fourth. So it must reduce to what's called the Poisson equation, which is Newton's law, but written in differential form. And that's exactly where that 8 pi g over c to the fourth comes from.
How do gravitational waves come into, are produced using your...
Field equations?
Yeah.
So gravitational waves are, what you basically say is, my space is approximately flat, but I have tiny little, what are called perturbations, to that flat space-time. And then you perturb Einstein's field equations, and you come up with the expression for what those perturbations are to your metric as a function of the distribution of the mass within my space-time at a far distance, is the mathy way to answer that. Yeah, I'm not sure I have a much better answer to that, though.
I have a different kind of question. How do I find the art wrap? Because I have students who want to do exactly this.
Email me. Yeah. So Katie Gabriel, trying to think. So she has a website, obviously, but I don't think she has any particularly useful information about this specific project that we have going on. But she's been really fantastic with this. She's made these really awesome notebooks for the students, journal all of their thoughts really as to how, because the idea is, I say here's some wacky thing like time dilation. Let's go figure out how to represent that. Right? And so it's a very open-ended, creative process on their side, and they come up with some really fascinating things. So yeah, I'd love to talk more about that.
So I'm interested in the idea that we can measure curvature of space like intrinsically from within the space. I think students would really like that idea.
Yeah.
How has that been experimentally measured? Is there experiments I can go look up to share about that?
Yeah, so in terms of, well, okay, so there's two like very famous ones. The one is this relativistic apsidal precession of Mercury, which is a prediction of general relativity. It's basically that Mercury's orbit is not exactly a closed ellipse. And there's a really funny history, not funny, there's a really interesting history about this where it was thought that there was this additional planet interior to Mercury called Vulcan that was creating this additional aberration that was measured. Turns out general relativity predicts that exactly. The other one is through what's called the Shapiro delay. So if I'm on the Earth, you can imagine taking a laser beam and shining it and bouncing it off of Venus or Mercury. And I actually had a slide on this and I didn't joke, but it turns out that in curved space, right, so the speed of light is the same at every local point, but the accumulated trajectory and the accumulated amount of time is actually going to be slightly longer than just the coordinate distance divided by the speed of light when space is curved. So what that means is that I say, okay, I'm going to shine my laser beam, I'm going to sit here and I'm going to watch. I'm going to look at my watch and I'm going to count the number of seconds that go by. And if I know the distance, the amount of time that I'm going to measure is actually going to be slightly longer than the amount of time it would be if space were flat, namely if the time was just the distance divided by the speed of light. And so those are the two like really, I think, well-known ones that I'm particularly aware of, but I'm not sure if that really answered what you wanted.
I think we'll take one more question, and then Eric will also be around during the coffee break. So if we didn't get to you, you can come up and talk to both of us. But we'll do one more. I think you had your hand up. Let me get you the mic. Or you have the mic. Okay, cool.
Right. We spend like a year of teaching geometry to our students, and we give them reasons why. But this year, this topic itself to me is like why we should do non-Euclidean geometry, so that we can make it an easy transition. Because you were saying here that time depends on space.
Time depends on, where you are in the presence of a gravitational
right.
field.
And the space that we're speaking of is not Euclidean, but non-Euclidean.
Yeah, that's right. Yeah, non-Euclidean geometry. Yeah, so Riemannian geometry, if you want to sound really fancy.
All right, let's thank Eric again. And we'll now go to our half-hour coffee break, and we'll be back here in 30 minutes at 10:55. So refreshments are out in the courtyard, I believe, and there'll be a big bell that rings when it's time to come back. So you hear the bell, start coming back for more cool science. See you then.